So today we are going to start with a new chapter called coordination compounds. Now before I come to coordination compounds, I want to talk about certain compounds. See, some compounds, saturated compounds, they combine together to form a compound which contain different types of ions. For example, KCl or K2SO4, Al2SO4, thrice 24H2O. Here potassium sulfate is there, aluminum sulfate is there, and 24 molecules of water of hydration is there. Then K4, Fe, CN6, another compound which contain potassium cyanide and iron cyanide. Then we have NH4 twice SO4, NH4 twice SO4, FeSO4, 6H2O, FeSO4, 6H2O. It contains ammonium sulfate, iron sulfate and water molecules. So these are compounds which contain more than one ions, and these are formed by the combination of 2 or 3 different type of compounds. Such compounds are called addition compounds or molecular compounds. See, addition compounds these all come under the category called addition compounds or molecular compounds. These addition compounds or molecular compounds are of different types. They are of 2 different types. First is complex compounds or coordination compounds. Coordination compounds, and 2 double salts. Now what are these? First I will come to double salts. See, some salts, if you dissolve in water, that molecular solids or addition solid compounds, when they are dissolved in water, they will split into corresponding ions. All those present in the solid state will dissolve and they produce all the ions present in it. For example, this potassium sulfate, K2SO4, Al2SO4, thrice 24H2O. You dissolve it in water, you will get potassium ions, aluminum ions and sulfate ions. Such type of compounds are called double salts. These are alums. This is potassium. Alum is a double salt. This is more salt, which is another double salt. You dissolve it in water, it will give you ammonium ion, Fe2 plus ion, sulfate ion, etc. Understood? So they are called double salts. Those compounds which split into ions, completely they split into ions, they are called double salts. Now you see this one, this compound. This you dissolve in water, you will get a potassium ions and this complex ion. They keep these compounds which contain this type of complex ions, they keep their identity in solid state as well as in aqueous or dissolved state. They keep their identity either in solid state or in solution, aqueous solution state also. If they keep their identity, that means if they are not splitting into corresponding ions, then we call them as coordination compound. And in P block elements we have seen, if you add ammonium solution to copper sulfate solution, you will get a deep blue colored solution. It is Cu NH3 4 times SO4. This is copper ammonium complex. It is a double salt. It is a coordination compound. Understood? So these compounds, they do not split into corresponding ions. So these are coordination compounds. Now we are coming into this detailed study of this coordination compounds. Now the first scientist who studied effectively successfully about the coordination compound is Alfred Werner. So he gave certain theory regarding this characteristics of coordination compound. They are called the Werner's theory. Now according to this theory, a metal is having two types of valencies. A metal has two types of valencies in coordination compounds. They are primary valencies and secondary valencies. They are called primary valencies and secondary valencies. So there is a compound COCl3 6NH3. This is a coordination compound. This substance, when it is dissolved in water, it gave precipitate. How you test for chloride ion? When you add silver nitrate solution, it will give a white curdy precipitate of silver chloride. When this was dissolved in water, it gave precipitate equivalent to 3 chloride ions. So that means these ions, chloride ions which are present there, they are ionizable. So these ions, these valencies, that is I told these valencies are satisfied by negatively charged ions and they are called primary valencies. So the primary valencies are satisfied by the negatively charged ions and they are ionizable. Whereas the metal is also having secondary valencies which are satisfied by either negatively charged or positively charged or neutral molecules. They are called the secondary valencies. So a metal atom or an ion has two different types of valencies in a complex or coordination compound. They are primary valencies and secondary valencies. Primary valencies are those which are satisfied by negatively charged ions because a metal will be having only positive charge. So these positive charge will be satisfied by the negatively charged ions and those are called the primary valencies. The secondary valencies are satisfied by either neutral molecule or negatively charged ions or positively charged ions. Now, the secondary valencies that will decide the geometry of the molecule. For example, I told you chloride ions, they are primary valencies. They do not give you they do not have any part in the fixing of geometry of the molecule. The geometry of the molecule is decided by this secondary valencies. And this atom is this compound cobalt is having 6 secondary valencies. So there are 6 secondary valencies means you know that if there are 6 paired electrons comes around a central atom, that will have an octahedral shape, isn't it? So cobalt, this molecule will have an octahedral shape. NH3, 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 then NH3, NH3. This is the secondary valencies. So around the cobalt there are 6 ammonia molecules. Ammonia molecules are there. They will fix the geometry of the molecule. The 3 chloride ions will be there like this. It will be there somewhere. They will not have any part in the geometry of the molecule. So this compound, it is here, the chloride ions are ionizable. They will give precipitate with the silver nitrate solution and that will be equivalent to 3 chloride ions. And these 6 ammonia molecules, they will fix they are satisfied the secondary valencies and they will fix the geometry of the molecule. Another example is Pt, NH3, CO NH3 4 times, CO NH3 4 times 3 plus. Here there are 4 secondary valencies. So it will have either tetrahedron or square planar structure. So like this, the secondary valencies alone will satisfy the or it will fix the geometry of the molecule. Now we come back to the different terms used in coordination compounds. So this is Werner's theory. We will come to the different terms used in coordination compound. The first one is the coordination entity or the complex. Coordination entity. coordination entity. The neutral molecules or ions along with the central metal atom, which is there in the square bracket, which are unionizable, that is called a coordination entity. For example, CO, NH3, 6 times Cl3. This is how that compound is written. These chloride ions are giving precipitate, they are ionizable. Now what is inside the square bracket? That is called the coordination entity. Here the coordination entity is CO, NH3, 6 times 3 plus ion. Isn't it? Because 1 chloride ion, 1 minus charge, 3 chloride ions, 3 negative charges. So this complex ion will have 3 positive charge. So therefore this is the coordination entity. Understood? And this is not ionizable. This part is not at all ionizable. We have suppose CO, Cl3, NH3, thrice. Suppose this is the coordination entity. This is negatively charged ion and this is neutral molecule. And this one, this will not give any precipitate with the silver nitrate because these chloride ions are inside the square bracket, in a coordination sphere. So it will not give any precipitate with the silver nitrate. Now since this chloride ion, that's the one which is written outside the square bracket, that is called the ionization sphere. This is called the ionization sphere. For example, CO, NH3, 5 times Cl, SO4. If you dissolve this ion, this complex compound in water, it will give a precipitate with the sulfate ion. That is, you add barium chloride, it will give a white precipitate with the white precipitate of barium sulfate. So this part is ionizable. So this is called ionization sphere and this is called the coordination sphere. Understood? So this is the coordination entity. Now next is the central atom. Here everywhere these neutral molecules or ions are arranged around a metal atom or ion. That is called the central metal atom or ion. Cobalt, here cobalt. I have written, we have seen copper ammonium complex, in that it is copper. Then silver chloride, if you add ammonium hydroxide, you get a silver ammonium complex. The silver is the central ion. So there will be a central metal atom or ion. Now next step is ligands. This is what we are studying for the first time. You are hearing it for the first time. Now what are ligands? Ligands are the neutral molecules or ions which are coordinated to the central metal atom. They are linked in a sigma bond, sigma linkage to the central metal atom. Now, how it is linked? See, the ligands, they are donating a pair of electrons. So the ligands must have at least one lone pair of electrons to donate. For example, we have seen ammonia molecule is having a lone pair of electrons. So it can donate this lone pair. In water molecule oxygen is having lone pairs of electrons. It can donate this lone pair. So it can act as a ligand. So the ligand must be able to donate at least one lone pair to the central metal atom. And where the central metal atom will accept it, it will accept it in empty orbitals. It can accept only in empty orbitals because an orbital can have only 2 electrons. So if a central atom has to accept 2 electrons, it must have empty orbitals. So the electrons, the pair of electrons donated by the ligand will be accepted in the empty orbitals of the central atom. So we have seen this example, CO, NH3, 6 times Cl3. Each of this ammonia molecule, each one will donate a pair of electron and form a coordinate linkage with the cobalt, metal ion. It will form a linkage. Each of the ammonia molecule will donate a pair of electron to form a bond with the cobalt. ion. Okay, but chloride ion is not like that. Only those in the ligands are donating a pair of electrons. That is why Mr. Gardner said these ligands are fixing. These neutral molecules or ions in the coordination sphere is fixing the geometry of the molecule. Now, ligands are of different types. Depending on the number of pairs it is donating or number of sigma bonds it is forming, we can classify them into monodendate, then di or bidentate, tridentate, tetradendate or even polydendate ligands are there. So first we will take monodendate ligands. Monodendate ligands means with the one lone pair it is catching. One monodendate ligand, that is, if the ligand is donating only a pair of electron to form a sigma bond with the central metal atom or ion, then we call it as a monodendate ligand. For example, ammonia molecule, then chloride ion, then water molecule. All of them can donate only a pair of electrons, so they are monodendate ligands. Understood? Then di or bidendate ligands. Didendate ligands. For example, ethylene diamine CH2, NH2, CH2, NH2. Ethylene diamine. Each of them are having this one. It is a didendate ligand. Oxalate ion, CO minus, CO minus. Here this oxygen can act as a ligand, a donor atom, so it is a ligand, it is a didendate ligand. So example for didendate or bidendate ligand is either ethylene diamine or this is a neutral molecule, that is an ion. Now we have tetradendate ligand, for example ethylene diamine tetraacetate, EDTA. It is ethylene diamine tetraacetate. Ethylene diamine means CH2, N, CH3, COO minus, CH3, COO minus, then CH2, N, again here also CH3, COO minus, CH3, COO minus. This is an hexadendate ligand. All the four oxygen atoms, these two nitrogen atoms, all can donate a lone pair. So it is a hexadendate ligand. So it comes under polydendate ligands. So we can say, we can classify the ligands into monodendate, didendate, tridendate, tetradendate and polydendate ligands are there. Depending on the number of sigma bonds it forms or number of lone pairs it is donating to form a sigma bond with the central metal atom or ion. Now we can again classify them into again different types. Now these didendate and polydendate ligands, they form a type of ligands called chelate ligands. Now what are chelate ligands? See, chelate ligands are those which forms a cyclic structure with the central metal atom or ion. For example, ethylene diamine. I write COEN twice. Cl2. CCO. Ethylene diamine is, I told you it is CH2, NH2, CH2, NH2. Both the nitrogen atoms in this NH2 group, they have lone pair of electron and say they donate. So we will write NH2. This lone pair is donating. Then CH2, CH2, NH2. It is forming a cyclic structure, isn't it? Again, NH2, CH2, CH2, NH2. See, cyclic structure is formed. Then we can say Cl, Cl, the positive charge. So this is forming a cyclic structure with the central metal atom or ion. So this type of ring structure or cyclic structure, if it is formed by a ligand, then we call it as a chelate ligand, and chelate ligand forms very stable compounds, cyclic structure, so they can form very stable coordination compound. So we can say this that monodentate they cannot form any chelate ligand, only if di or afterwards that they can form this type of cyclic structure with the central metal atom or ion, and this type of ligands are called chelate ligands. Okay, now we will come to another classification. Ligands which can form bond with the central metal atom with more than one atom, they are called ambidentate ligands. For example, Cn and Nc. In this, carbon and nitrogen, both of them can act as donors. So we call them as ambidentate ligands. NO2 and NO, ONA. It is another ambidentate ligand. Here nitrogen is acting as the donor atom, here oxygen is acting as the donor atom. So this type of ligands are called ambidentate ligands. Thiocyanate and isothiocyanate, SCN and NCS, they are all ambidentate ligands. Ambidentate ligands. That is, more than one atom can act as a donor atom. So we call them as ambidentate ligands. So we can classify ligands like this. Now next is coordination number. What is coordination number? See, the number of ligands attached to a central metal atom is called, in the coordination sphere, is called the coordination number. For example, CO, NH3, 4 times Cl2 plus. This is a coordination, coordinate compound ion or complex ion. How many ligands are attached? 4 plus 2, 6 ligands are attached. So the coordination number is 6. Understood? Now PT, NH3 twice, Cl2. How many ligands are attached? 2 plus 2, 4 ligands. So the coordination number is 4. Now another is CO, En twice, Cl2 plus. Now here, see, En is ethylene diamine. For ethylene diamine, it's a didentate ligand. So we will have to take it as 2 ligands. So 1 ethylene diamine, 2 ligands. 2 ethylene diamine, 4 ligands. 4 plus 2, 6. Coordination number is 6. Okay, so this is the number of ligands attached to the central metal atom or ion. So if it is a didentate ligand, we will have to consider it as 2 ligands. If it is a tridentate ligand, we will have to consider it as 3 ligands, like that. Understood? So we can find out the coordination number. Now the oxidation number of the central metal atom. You see, the central metal atom has an oxidation number. For example, here, we don't know the oxidation state of cobalt. Put it as X plus. Ammonia molecule, it is a neutral molecule, so oxidation number is 0. Oxidation number is 0. 0 into 4 plus 1 chloride ion, it is minus 1. 2 chloride ion into 2. The total charge is plus, so the net charge is plus 1. So what is X? X plus 0 plus minus 2 is equal to plus 1. So what is X? X is equal to 1 plus 2. So that is 3. That is plus 3 is the oxidation state of the central cobalt atom. What about platinum? PT? PT is X, we don't know. Ammonia molecule 0 into 2 plus 1 chloride ion minus 1 into 2. And what is the net charge? It is 0 here. It is equal to 0. So X plus 0 plus Minus 2 is equal to 0. So X is equal to 2. So here oxidation number of the central metal ion is plus 2. What about this one? NiCO 4 times. What is the oxidation state of the central metal atom here? Metal atom or ion? Carbon monoxide. So it is 0. 0 into 4 plus we don't know this, put it as X is equal to, it's a neutral molecule. So total of the oxidation state is equal to 0. So what is X is equal to 0. So it is 0 oxidation state. Understood? So this is about the oxidation state of the central metal atom. Now, there are two different types of complexes, homolytic and heterolytic coordination compounds. Now, what are homolytic and heterolytic? Now, what is homolytic? If a complex compound contain only one type of ligand, then we call it as a homolytic ligand. For example, CO, NH3, 6 times